A French magazine from 1931 lies open on an imagined table, its pages the color of old cream, the paper thin enough that the print from the reverse side bleeds faintly through. The letters column is dense with small typeface, the kind of type that requires good light and a willingness to lean in, each line compressed tightly against the next, as though space on the page was something the editors were rationing. There are advertisements along the margins for radio components, for correspondence chess clubs, for something called a pocket encyclopedia, and between them, pressed in among the ordinary reader correspondence of a popular science fiction periodical, a letter that raises a question about murder and ancestry and the logical structure of time. The magazine is Asterisk Sciences et Voyages, asterisk. The year is 1931, and the question being asked in that letter column, in whatever particular phrasing a French reader of pulp science fiction used to pose it, is the same question that would later find its way into peer-reviewed physics journals, into the working papers of some of the 20th century's most careful thinkers, and into the plots of films that audiences watched in darkened cinemas more than 50 years after that first printed exchange. The question is simple enough to state in one sentence. If a person could travel backwards in time, and if that person killed their own grandfather before the grandfather had produced any children, would the person exist to make the journey at all? That is the question. It sounds at first like a puzzle. It turns out to be something more particular than that. The pages of Asterisk Sciences et Voyage, asterisk smelled of ink and something faintly mineral, the way old paper does when it has been stored in a building that has absorbed a century of damp and warmth and cold in its walls. The readers who wrote to that column were enthusiasts, people who followed the literature of science fiction with genuine attention, who thought about the implications of the futures being described, who were willing to pose uncomfortable questions in public print about what would and would not logically hold together. The question about the grandfather did not come from a physicist. It came from someone reading a magazine on an ordinary day, thinking carefully about a story, and noticing that something in it did not quite resolve. The word for what they had noticed is paradox, not in the casual sense of something seeming contradictory but not quite being so, not in the loose conversational sense of an apparent tension that dissolves on examination. The grandfather paradox is a paradox in the strict sense, a logical structure in which two mutually necessary conditions cannot both be true and cannot both be false, and produce by their interaction a cycle that has no stable resting point. The traveler kills the grandfather. The grandfather produces no children. The traveler is never born. No traveler goes back. The grandfather lives. The grandfather produces children. The traveler is born. The traveler goes back and kills the grandfather. The grandfather produces no children. There is no step in that sequence where the logic stops and rests. Each conclusion produces the conditions for its own negation, which produces the conditions for the original conclusion, which produces the conditions for the negation again. A circle, an arrow marking a direction of travel, the arrowhead arriving back at its own origin and pointing into the line it has already drawn. It is worth pausing on what kind of thing this is before going any further. A simple logical contradiction, the claim that something is both true and false at the same time, can be dismissed immediately because it violates the most basic condition of rational discourse. If someone writes two sentences on a chalkboard, one asserting that a given object is red, and the other asserting that the same object is not red, the contradiction is immediately visible, immediately stable in its wrongness, and immediately resolvable by pointing to the error. The sentences are static. They do not interact. They do not produce consequences that cycle back through the conditions of their own assertion. The grandfather paradox is different from this. It is not two sentences written side by side and shown to be incompatible. It is a process that unfolds across time, each event causing the next, and the sequence of causation eventually curves back to undermine the conditions that started it. The contradiction is not between two statements, but between two moments in a chain of events that, if time travel is possible, forms a closed loop with no external point of entry. This is why the grandfather paradox cannot be set aside the way a static logical contradiction can be set aside. It does not live in language. It lives potentially in the structure of physical causation, which means that if time travel were possible, the paradox would not be a problem of logic to be cleared up with careful phrasing. It would be a problem of physics. It would require resolution at the level of what the universe actually allows. But that understanding took time to develop. In 1931, in a letters column in a French science fiction magazine, it was still just a question that a reader had noticed. And for another 12 years, it remained in the domain of fiction. In 1943, a French writer and filmmaker named René Barjavel published a novel called * Le Voyageur Imprudent, which translates approximately as the imprudent traveler or the thoughtless traveler, depending on how one renders the faint moral weight the title places on the adjective. The novel follows a scientist named Saint Menu, who has developed a device called the anachron, a compound from the Greek for against and time, a machine whose name announces its purpose and its dangers simultaneously. Saint Menu uses the anachron to travel through time, and in doing so, he inadvertently enters the ancestral past in a way that threatens the line of people whose accumulating existence produced him. The novel is not primarily a technical treatise. It is a story, but Barjavel places the logical problem of the grandfather paradox at the structural center of the narrative, not as a background puzzle, but as the central mechanism of what goes wrong. The anachron sits in whatever room Barjavel imagined for it. Brass fittings, glass panels, dials that measure something other than temperature or pressure, a device whose purpose is written into its form, even if its form is never described in precise technical terms, because 1943 did not have a precise technical vocabulary for time machines any more than 1895 had. Saint Menu stands beside it at the moment before a journey, and somewhere in the past of the novel's world, the chain of events that produced him is already in motion, already dependent on the particular sequence of meetings and survivals and ordinary unremarked moments that will eventually result in him standing where he stands. The anachron has dials that do not yet indicate anything dangerous. They will. Barjavel was writing in occupied France during the Second World War, which gives * Le Voyageur Imprudent a context that its plot does not directly acknowledge, but cannot be entirely separated from. The idea of a traveler who interferes with the past and destroys the conditions for his own existence, who, with the best or worst, or simply the careless intentions, eliminates what produced him, carried particular resonance in a country whose familiar world had been altered in ways that felt irreversible. Whether Barjavel intended this resonance or simply happened upon the grandfather paradox as a narrative mechanism is not clear. What is clear is that he recognized in it something more than a logical puzzle. He saw it as a story, and in making it a story, in giving the paradox a character, a device, a name for the machine, a moral inflection in the title, he did something that the letter column of * sciences, Eliage's * could not quite accomplish. He made the problem feel like something that had consequences. The novel was not widely read outside France for several decades. The paradox it placed at its center continued to be discussed in science fiction circles, in philosophy seminars, in the kind of informal intellectual conversations that do not leave records. It accrued names. The grandfather paradox became the standard formulation, though some discussions used variants: the grandmother paradox, the ancestor paradox, the parent paradox, each of which adjusts the specific relationship while preserving the essential logical structure. The grandfather version became canonical, not because grandfathers are uniquely important in the logic of ancestry, but because the relationship is distant enough to feel abstract and close enough to feel personal, which is perhaps the right distance for a thought experiment to inhabit. Thought experiments have a particular role in physics and philosophy that is easy to underestimate. They are not substitutes for evidence. They do not produce data. What they produce is clarity about what is at stake, about which specific feature of a problem is generating the difficulty, and what would have to be true for the difficulty to be resolved. The grandfather paradox, framed correctly as a thought experiment, isolates exactly one question: whether a consistent causal history can exist when a loop of causation curves back to undermine the conditions that started it. Everything else about the scenario, the method of time travel, the specific historical period visited, the relationship between traveler and ancestor, is scaffolding. Strip it away, and what remains is the question of causal consistency in closed loops. That is a physics question. It took physicists a while to recognize it as such. The recognition, when it came, arrived in the form of a paper. David Deutsch published a paper in 1991 in Physical Review D, one of the primary journals for theoretical physics, titled in the direct manner of academic science, and addressed to the problem of the quantum mechanics of closed time-like curves. Closed time-like curves are what general relativity calls the paths through spacetime that loop back to their own starting point, paths that, if a traveler could follow them, would return the traveler to a moment in their own past. The name is technical, but the concept is exactly what the grandfather paradox describes: a loop in time. Deutsch used the grandfather paradox specifically to frame the problem of consistency. His paper addressed the question of whether quantum mechanics could describe what happened to a system traveling along such a loop in a way that did not produce a logical contradiction. The grandfather paradox was not, in that paper, a piece of literary curiosity or a philosophical thought experiment borrowed from pulp fiction. It was a named physical problem requiring a mathematical answer. The shelf in a university physics library that holds the 1991 issues of Physical Review D. Is not a dramatic shelf. The journals are thick. Their covers a standard institutional design, their spines aligned with the particular regularity of publications that have been bound and shelved by librarians, whose interest is in preserving the record rather than displaying it. The paper by Deutsch sits in one of those issues, its pages no different from the pages around it, double columns of equations and prose, the argument laid out with the careful internal structure of a professional physics paper, its conclusions expressed in the qualified, precise language that journals require. But the problem it addresses traces a direct line back to that letters column in asterisk. Sciences at Voyages asterisk, back to Saint Manu and the Anachron, back to the reader who sat with a pulp magazine and asked what would happen if someone went back and killed their grandfather. That line from 1931 to 1991 is not a straight one. It bends through fiction and philosophy, through decades during which the question was considered too speculative for serious scientific attention, through the gradual shift in physics culture that allowed topics once considered disreputable to be examined in peer-reviewed contexts when the mathematics turned out to be genuinely interesting. The grandfather paradox did not become a physics problem because physicists decided to dignify a science fiction idea. It became a physics problem because the mathematics of general relativity turned out to permit, without ruling out, structures in space-time that would make the paradox's causal loop physically realizable rather than merely imagined. Once those structures appeared in the equations, the grandfather paradox was no longer a story problem. It was a constraint on what any consistent physical theory would need to accommodate. Deutsch's adoption of the paradox into Physical Review D** was not the first time the physics community had engaged with it, but it was a significant moment in the formalization of the engagement. The paper treated the grandfather paradox, the way physics treats any foundational problem, as a condition that any viable theory must satisfy, a test case against which proposed descriptions of physical reality must be checked. If a theory of quantum mechanics applied to closed time-like curves produced, as a consequence, a grandfather paradox-style logical contradiction, then the theory was incomplete or wrong. The paradox had become a benchmark, two sentences on a chalkboard written in the same hand. The first, the traveler exists. The second, the traveler cannot exist. Neither sentence can be erased without erasing the reason for writing the other. The chalkboard is not a classroom exercise. It is a description of an actual constraint on physical law. What makes the grandfather paradox particularly resistant to easy dismissal is precisely this dynamic quality. The way the contradiction is not static, but generative. Most logical paradoxes, once carefully examined, dissolve. The apparent contradiction turns out to be a result of ambiguous language, or of a hidden assumption that can be named and discarded, or of a category error that becomes visible when the terms are defined precisely. The grandfather paradox does not dissolve in this way. The careful examination does not reveal a hidden assumption that can simply be named and removed. It reveals that the contradiction is structural, built into the relationship between causation and temporal sequence that makes the loop a loop rather than a line. A causal sequence on a line is not paradoxical. Event A produces event B, which produces event C. The causes precede their effects. The sequence is asymmetric. Nothing in it curves back to undermine the conditions that started the chain. This is how causation ordinarily works, and ordinary causation does not produce paradoxes of this kind. What the grandfather paradox requires, what time travel requires, if it involves traveling to a past that can be altered, is that causation operate not along a line, but along a loop. The traveler's action in the past is caused by events in the future, the traveler's existence, the development of time travel technology, the decision to use it, and the outcome of that action in the past then affects the very events in the future that caused it. The loop has no beginning and no end. The cause is downstream of its own effect. This is not a feature of ordinary causation that appears anywhere in everyday experience, which is part of why the paradox has remained productive as a problem rather than being solved quickly and set aside. To understand how strange this is, consider what it means for something to be caused. In ordinary experience, causes come before effects. The billiard ball strikes another ball because someone hit it with a cue before the collision, not after. The glass falls from the table because it was pushed, and the pushing happened before the falling. This before-after structure, temporal priority of the cause, is so embedded in how physical reasoning works that it functions more like a background assumption than a stated principle. The grandfather paradox attacks that background assumption directly. It asks what happens when a cause can, through the mechanism of time travel, depend for its own existence on the effect it is about to produce. The answer is not a clean logical contradiction that dissolves on inspection. The answer is a loop. The loop is what makes the problem a problem. The French science fiction readers of 1931 who raised this question in the letters column of Sciences et Voyages were not, presumably, thinking about temporal priority in causal sequences or the conditions under which physical law must be self-consistent. They were thinking about a story and noticing that something in it produced an uncomfortable circularity. But the circularity they noticed was the real one. The discomfort was appropriate. The question they were asking turned out to be genuine, in the sense that it could not be answered by a moment's careful thought and then filed away. It remained open across the decade of Barjavel's novel, across the decades of informal discussion that followed, across the decades during which physics developed the mathematical structures that made the question formally precise, and into the 1991 issue of Physical Review D*, where Deutsch brought it to bear on quantum mechanical descriptions of spacetime. It remained open in various forms after that paper too. The image of a circle drawn on paper is the right image for all of this. Not a complex diagram, not a multi-dimensional mathematical structure rendered in unfamiliar notation. A circle, an arrow on the circle indicating the direction of travel. Yrkthusti, the arrowhead arriving back at the point where the line began, pointing into the line already drawn. That is the paradox in its simplest and most honest form. The traveler moves along the arrow points forward, the forward direction curves, and then the arrowhead meets the origin of the line it has been drawing, and the question becomes, does the loop close? And if it does, what happens inside it? A circle drawn on paper does not answer the question. It states it. The statement is simple. The answer, as the next 60 years of physics and philosophy demonstrated, is neither simple nor settled, though it is genuinely interesting in ways that continue to reward careful attention. One of the reasons the grandfather paradox has retained its vitality as a problem is that it sits at the intersection of several domains that do not ordinarily share territory. Logic has one set of tools for thinking about self-defeating propositions. Philosophy has another set of tools for thinking about personal identity and what it means for a person to continue to exist across time, which the paradox implicates in its specific focus on ancestry and existence. Physics has the mathematical machinery of general relativity and quantum mechanics, both of which bear on the question in different and not entirely compatible ways. Fiction has the narrative ability to make abstract structures feel consequential, to give the loop a face and a name, and a brass machine with glass panels, and a moral weight expressed through a title. None of these domains, on its own, has fully resolved the question. The grandfather paradox has persisted, in part because it requires all of them to work together, and they do not work together easily. What Barjavel understood in 1943, writing a novel rather than a physics paper, was that the grandfather paradox is not just a problem about time. It is a problem about what it means for a causal history to be coherent. Saint Menu, standing beside the Anacron in whatever room the novel places him, is not simply a character in a science fiction story. He is the embodiment of a question about whether the structure of time can sustain a loop without collapsing. The novel does not answer the question because novels do not answer physics questions. What it does is give the question a form in which the stakes are legible: a person, a machine, a past that is being threatened, a future that depends on that past remaining intact. That legibility matters. The grandfather paradox has moved through intellectual culture, not primarily through academic papers, though the papers are where the formal work has been done, but through stories and thought experiments and the kind of informal reasoning that people do when they encounter a problem that does not have an obvious solution. The 1931 letter column made the question legible in print. Barjavel's novel gave it narrative form. Later works, novels, films, philosophical essays, popular science books, extended and varied the form while preserving the essential structure. The loop, the ancestor, the traveler, the arrow, arriving back at its own origin. The consistency of the structure across all these different forms is itself worth noting. The grandfather paradox did not evolve into something different as it passed through different hands. It remained stable. The scenario changed. The relationship between traveler and ancestor, the method of time travel, the period visited, but the logical core did not change. The cause that depends on its own effect. The loop with no stable resting point. The two sentences on the chalkboard that cannot both be erased without erasing the reason for writing them. The stability suggests that the paradox is touching something genuine in the structure of the problem, rather than being an artifact of a particular way of framing it. Genuine problems tend to remain recognizable across different formulations, different context, different scales. The grandfather paradox has been formulated in terms of ancestors and time travelers, in terms of billiard balls sent through wormholes to collide with their earlier selves, in terms of quantum mechanical density matrices and self-consistency conditions. In each formulation, the same core problem appears: a closed causal loop, a question about whether consistency is possible, a demand for resolution at the level of what the universe actually permits, rather than at the level of linguistic clarification. The small type of the 1931 letters column contained all of this, compressed into the space available between the advertisements for radio equipment and correspondence chess clubs. The reader who wrote the question almost certainly did not know they were beginning something that would last for decades and travel across disciplines and find its way into journals that did not yet exist at the time of writing. They noticed a logical difficulty and wrote it down. The magazine printed it. The question was released into the record. Barjavel's anachron, with its dials and its glass and its brass fittings, stands in the pages of a 1943 novel as the physical embodiment of that released question. The device does not move in the image. Its dials are still, its panels clean. Saint Menu beside it at the moment before any journey has been made. The past is intact. The ancestral line is unbroken. Everything that produced Saint Menu is where it should be, in whatever unspecified arrangement of meetings and survivals the novel's world required to result in him. The anachron has not yet done anything, but the title of the novel is already a warning. Asterisk. Le voyageur imprudent. Asterisk. The traveler who does not think carefully enough before going. The traveler who does not understand what the loop contains before entering it. 12 years before that novel, in a magazine between advertisements, 48 years after the novel, in a physics journal on a library shelf. The question remained the same across all of it. The loop does not resolve. The arrow arrives at its own origin. The arrowhead points into the line it drew, a circle on paper, an arrow. The direction of travel is indicated clearly. The end point of the arrow is the starting point of the arrow. There is a pleasant, quiet, unresolvable quality to this image, pleasant in the way that a very clean statement of a genuine difficulty can be pleasant. The kind of feeling that arrives when a problem has been stated precisely enough that the actual difficulty is fully visible rather than obscured by imprecision or conflated with something easier. The difficulty is visible. The loop is drawn. The arrow curves all the way back to where it started, and the question of what happens there, whether the loop can close, whether consistency demands that it not close, whether the universe has a way of preventing the arrow from arriving, whether the arrow arrives and the loop closes and something stranger than contradiction follows, is a question that the circle on the paper is not able to answer. The circle simply holds it, quietly, in its closed shape. The arrow simply points forward and around and back to the beginning, indicating a direction of travel through a loop that cannot be completed in the ordinary way. And there is something restful, in its own way, about a question that is stated this cleanly, not resolved, stated. The statement does not demand anything. It does not insist on an answer before the night is over. It sits in its circle, its arrow indicating the direction, the arrowhead back at the origin, and rests there in the same pleasant open condition that a reader of Asterisk Sciences et Voyages Asterix might have felt in 1931, somewhere between an advertisement for radio components and one for a correspondence chess club, reading a letter about killing a grandfather and thinking that is odd and precise, and I am not sure what the answer is, and the not knowing is not uncomfortable. It is the specific comfortable quality of a question that is genuinely interesting. The circle is complete. The answer is not. Both of these things can be true at the same time, and there is nothing in that simultaneous truth that requires resolution before sleep. 4 cesium atomic clocks were loaded into the overhead compartments of a commercial passenger aircraft at Dulles International Airport in October of 1971. They were compact metal instruments, unremarkable to look at. The other passengers, boarding with their coats over their arms and their tickets folded in their breast pockets, would have noticed nothing unusual about the cases being stowed. The clocks were already ticking. They had been ticking before they were carried through the terminal, before they passed the check-in desks, before the physicist Joseph Hafele and Richard Keating had driven them out to the airport in the early hours of the morning. They would continue ticking as the aircraft pushed back from the gate and turned toward the runway and lifted into the October sky. What the clocks were doing, in the most precise terms available at the time, was measuring the passage of time. Cesium atomic clocks measure time by counting the oscillations of cesium-133 atoms as they transition between two specific energy states, and in 1971, they were the most accurate timekeepers ever built. The frequency of those oscillations is stable enough that a cesium clock will neither gain nor lose more than a second over the course of roughly 300,000 years. Hafele and Keating were not interested in what the clocks measured over 300,000 years. They were interested in what the clocks would measure over the course of a single round-the-world flight, and how those measurements would compare to identical clocks left behind on the ground in Washington. Einstein's special theory of relativity, published in 1905, had predicted that a clock moving at high speed through space would run more slowly than a clock at rest, a phenomenon called time dilation. His general theory, published a decade later, had added a related prediction. A clock in a weaker gravitational field would run faster than one in a stronger field. An aircraft flying at cruising altitude is both moving faster than the ground and sitting in a slightly weaker gravitational field because it is farther from the center of Earth. Both effects are present simultaneously, and they pull in opposite directions. The velocity slows the airborne clock. The reduced gravity speeds it up. The relative sizes of these competing effects depend on the direction of travel and the altitude, and they are not large. But by 1971, Cesium atomic clocks were precise enough to measure them. When the eastward flight returned, and Hoffele and Keating compared their airborne clocks to the reference clocks on the ground, the airborne clocks had lost approximately 59 nanoseconds. When the westward flight returned, the airborne clocks had gained approximately 273 nanoseconds. Both results were consistent with Einstein's predictions to within about 10%, within the margin of the instrument's own measurement uncertainty. A nanosecond is 1/1000th of a second. The amount of time lost or gained was too small to matter for any ordinary human purpose, but it was real, it was measured, and it was exactly what the equations had said it would be. The experiment mattered not because of the numbers. 59 nanoseconds is not a span that changes anything for the people on the aircraft, but because of what the numbers confirmed. Time, the experiment showed, is not a fixed background against which events occur at the same rate everywhere in the universe. It is a quantity that changes depending on how fast a clock is moving and where in a gravitational field that clock sits. Two clocks that start the day showing the same time will, if one is flown around the world and the other is not, show different times when they are compared again. The difference is small. It is also real. The rotating of Earth already imposes a small effect on the westbound versus eastbound flights, because the surface beneath the aircraft is moving. Flying westward against Earth's rotation reduces the aircraft's velocity relative to the inertial frame in which the gravitational calculation is made, while flying eastward with Earth's rotation increases it. This is why the westbound flight gained time, while the eastbound flight lost it. The relativistic effects did not cancel, but shifted, each flight giving a different balance of the two competing corrections. Hafeitu and Keating published their results in the journal Science in 1972, and the paper became a standard citation in discussions of experimental confirmation of special and general relativity. The clocks themselves were eventually returned to their cases and stored. The numbers they had recorded were passed along to the wider physics community, and over the following decades into textbooks and lecture notes and popular science writing. The experiment was not at the time presented as remarkable in the way that a new discovery tends to be. It was described, even in the original paper, more in the manner of a confirmation, an experiment designed to check a prediction that the theory had been making for 66 years, and that the theory had now, once more, passed. There is a version of the same experiment running continuously today, in orbit, at an altitude where the effects are large enough to matter in a practical sense. The global positioning system relies on a constellation of satellites, each carrying atomic clocks, whose signals are combined by receivers on the ground to determine position. The satellites orbit at approximately 20,200 kilometers above Earth's surface, and at that altitude, the reduced gravitational pull causes their clocks to run faster than ground clocks by about 45 microseconds per day. Their orbital velocity at roughly 14,000 kilometers per hour causes their clocks to run slower than ground clocks by about 7 microseconds per day. The net effect is a daily gain of approximately 38 microseconds per satellite. If the engineers who designed the system had ignored these effects, the position errors they would introduce would accumulate at a rate of roughly 10 kilometers per day, rendering the system useless. The corrections are applied. The maps remain accurate to within a few meters. The relativistic adjustment is not a theoretical nicety, but an operational requirement that has been built into the system's functioning since the first satellites were launched. A muon is a subatomic particle similar to an electron, but about 200 times heavier. It is unstable. Left to its own devices, A muon will decay into an electron and two neutrinos with a mean lifetime of approximately 2.2 microseconds. This is a very short time. 2.2 microseconds is 2 millionths of a second, and in that span of time, even a particle traveling at nearly the speed of light can cover only about 660 meters before it disappears. The muons that matter to this account are not produced in laboratories. They are produced in the upper atmosphere at altitudes of roughly 10 to 15 kilometers, when high-energy cosmic ray particles collide with the nuclei of air molecules. The collision sprays secondary particles downward, and among them are large numbers of muons. These muons are traveling at velocities of 99.7% of the speed of light or more. At that speed, the calculation seems to work against them. Even at the speed of light, a muon with a 2.2 microsecond lifetime should be able to travel only about 660 meters before decaying. The distance from the upper atmosphere to Earth's surface is approximately 15 kilometers. By straightforward arithmetic, essentially none of these muons should arrive at the ground. Detectors at sea level, however, detect them in large numbers. The muons complete a journey that their rest frame lifetimes should make impossible. The resolution is time dilation. A muon moving at 99.7% of the speed of light experiences time passing at a rate that is more than 20 times slower than time in the frame of an observer at rest on the ground. From the muon's perspective, its lifetime is still 2.2 microseconds. That is simply how long muons live. But from the ground's perspective, that 2.2 microseconds has been stretched by the Lorentz factor into something closer to 50 microseconds. 50 microseconds at nearly the speed of light is enough time to cross 15 kilometers and reach the detector. The muon is not defying its own decay rate. It is experiencing its decay rate in its own time frame, while the ground's time frame records something different. The detection of atmospheric muons at sea level is not an occasional or uncertain result. It is a repeatable measurement, replicated at many facilities, and consistent with the predictions of special relativity at every velocity at which the measurement has been made. The muons arrive because time runs differently for them than for the clocks on the ground. This is the same phenomenon Hefele and Keating measured with atomic clocks on aircraft, scaled up to a regime where the effect is large enough to transform an impossible journey into a completed one. Muon decay has also been measured precisely at particle accelerator facilities, including CERN, where muons are produced and accelerated to known velocities in controlled conditions. The measured lifetimes of high-velocity muons in these experiments match the Lorentz factor calculated from their velocities with high precision, extending the atmospheric observation into a domain where the experimental parameters can be set and varied deliberately. The result is the same at every speed tested. The faster the muon moves, the longer it lives, and the extension matches the formula Einstein wrote down in 1905. Kurt Gödel arrived at the Institute for Advanced Study in Princeton in 1933 and remained there for the rest of his life. He was known primarily as a mathematician and logician, the author of the incompleteness theorems, which had established in 1931 that any formal mathematical system, complex enough to contain arithmetic, would also contain true statements that the system could not prove from within itself. In 1949, Gödel published a paper in a volume assembled to honor Einstein's 70th birthday. The paper was a contribution to physics rather than logic, and what it contained was a solution to Einstein's field equations, the set of equations at the center of general relativity, which relate the geometry of space-time to the distribution of mass and energy within it. Gödel's solution described a universe that rotated as a whole, It was mathematically coherent. It satisfied the field equations exactly. And it had a consequence that Gödel himself noted in the paper. In a uniformly rotating universe of this kind, closed time-like curves would exist everywhere in spacetime. A closed time-like curve is a path through spacetime that loops back to its own starting point without ever requiring a traveler along it to move faster than light. In Gödel's rotating universe, the rotation of spacetime itself would drag future-pointing paths around until they curved back into the past. A traveler who followed such a path long enough would return to the moment and place from which they had departed. They would not have moved backward in time from their own perspective. They would simply have followed a continuous path through space-time that happened to end where it began. The implication is significant. It means that in a universe with Gödel's geometry, the distinction between past and future, the sense that the past is fixed and the future is open, would not hold globally. The same space-time geometry that permits a traveler to move forward into what they experience as the future would also, if they traveled far enough in the right direction, bring them back to what they had previously experienced as the past. Gödel noted this consequence without apparent alarm and with the particular satisfaction of someone who has discovered that a set of constraints, followed carefully to their conclusion, yields something unexpected. Einstein, who was present in Princeton when Gödel handed him the paper, wrote a response acknowledging the mathematical validity of the solution. His published response, included in the same volume, noted that Gödel's rotating universe was a legitimate solution to the field equations. He then suggested that physical considerations, the actual conditions of the observed universe, would rule out such solutions in practice. The universe, as far as observational evidence then showed, was not rotating in the way Gödel's solution required. Einstein was not dismissing the mathematics. He was suggesting that the mathematics described a universe that was not the one they both inhabited, and that the physical universe might have properties that excluded, rather than included, the troubling geometry. This response is itself a kind of data point. The most careful physicist of the century felt the need to respond to a mathematical demonstration that his own equations permitted time loops, and the response was not dismissal, but a careful effort to locate the physical constraint that might prevent them. The year of Gödel's paper was also the year that Einstein turned 70. He had lived long enough to see his own equations return this result, and to need to write publicly about why he thought it did not threaten the structure of the universe he understood. The two men continued to walk together across the Princeton campus in the years that followed, talking, according to those who observed them, about philosophy and physics and the nature of time. What they said to each other on those walks was not recorded. Frank Tipler was a physicist at Tulane University when he published a paper in Physical Review D, in 1974, demonstrating another route to closed time-like curves. Tipler's construction was less abstract than Gödel's rotating universe. It specified a physical object, an infinitely long massive cylinder, rotating at approximately half the speed of light. If such a cylinder existed, the space-time geometry around it would be distorted in a way that produced closed time-like curves in the region surrounding the rotating mass. A spaceship maneuvering in that region could, by following a carefully chosen path around the cylinder, complete a trajectory that returned it to an earlier moment in time. The cylinder Tipler described is not something that could be built. Infinite length is not a property any physical object can possess. The mass density required to produce the necessary space-time distortion would exceed that of any known material by many orders of magnitude. The energy required to set the cylinder rotating at half the speed of light would, and even a finite approximation of infinite length, be effectively unbounded. Tipler was not proposing an engineering project. He was doing what theoretical physicists do, exploring the full space of what the equations permit, without constraining the exploration to the limits of current technology or available materials. What the paper showed was that Einstein's field equations, applied to a different configuration of mass and rotation than Gödel had used, again produced closed time-like curves. The equations permitted them, repeatedly, under a range of conditions, whenever the geometry of spacetime was distorted in certain ways by the distribution and motion of mass. This was not a coincidence or an artifact of a particular unusual choice of coordinates. It was a structural feature of the theory. General relativity, built to describe gravity and the curvature of spacetime, turned out to contain within it the mathematical possibility of paths through spacetime that looped backward in time, not as an aberration, but as a consequence of the same geometry that described the orbit of Mercury and the bending of starlight around the sun. The question that Tipler's paper, like Gödel's, left open was not whether such solutions existed mathematically. They clearly did. The question was whether the universe would permit them to be realized physically, or whether some additional principle, not yet identified, would always prevent them from forming. In the summer of 1985, Carl Sagan was finishing the manuscript of a novel. Sagan was an astronomer and science communicator who had spent his career thinking carefully about questions at the boundary between what was known and what was merely imaginable, and the novel he was writing, which would be published in 1985 as Contact Asterisk, required his protagonist to travel enormous distances through space in a very short time. Sagan wanted the mechanism of her travel to be physically plausible, or at least not obviously impossible, and so he sent a draft to a colleague and friend, the physicist Kip Thorne at Caltech, and asked whether a traversable wormhole might serve as a credible mechanism for the story. Thorne read the draft. Then he sat down with his colleagues Michael Morris and Ulvi Yurtsever and worked through the mathematics. The question of whether a traversable wormhole was physically possible was one that had not been examined carefully in the peer-reviewed literature, and Thorne found the mathematics worth pursuing beyond what Sagan had asked. What the calculations produced, when they were published in Asterisk Physical Review Letters, Asterisk in 1988, was a detailed analysis of the conditions under which a wormhole connecting two separate regions of spacetime could remain open long enough to be traversed. A wormhole is a concept with a long mathematical history. The Einstein-Rosen bridge, identified by Einstein and Nathan Rosen in a 1935 paper, was an early form of the idea, a connection between two separate regions of spacetime that appears in certain solutions to the field equations. But the Einstein-Rosen bridge was not traversable. Any attempt to pass through it would cause it to collapse before the traveler reached the other side. What Thorne, Morris, and Yurtsever were asking was whether a different configuration, one designed specifically to remain open, could satisfy the field equations. The answer the paper provided was yes, with a condition: a traversable wormhole, one whose throat remained open long enough for a traveler to pass through, would require matter with negative energy density to line its interior. This is not a material that appears in ordinary experience. Ordinary matter has positive energy density. Its energy, measured in any frame, is a positive number. Matter with negative energy density has, in the relevant sense, less than nothing. Its presence in a region of spacetime has the effect of pushing outward rather than pulling inward, which is what is needed to keep the wormhole throat from collapsing under its own gravitational tendency. The condition is precise. The amount of negative energy density required and its distribution along the wormhole throat can be specified mathematically. Whether matter with negative energy density can exist in nature is a separate question, and it has a careful answer. Quantum mechanics permits it in certain restricted circumstances. The Casimir effect, a measurable attractive force between two closely spaced, uncharged metal plates in a vacuum, arises because the plates suppress the quantum vacuum fluctuations in the space between them, producing a region where the effective energy density is lower than the vacuum baseline. In a precise sense, this is a region of negative energy density relative to the surrounding space. It has been measured. The force is real and has been confirmed by experiment. Whether the Casimir effect or any similar quantum phenomenon could produce negative energy density at the scale and distribution required to keep a macroscopic wormhole open is a separate question, and the answer is that no known physical process comes remotely close to the requirement. The mathematics says what is needed. The engineering gap between what is needed and what is available is not small. Thorne and his colleagues then extended the analysis in a direction that Sagan had not specifically requested. They noted that a traversable wormhole connecting two separate regions of spacetime could, under certain conditions, be converted into a time machine. The mechanism is straightforward in principle. If one mouth of the wormhole is accelerated to high velocity relative to the other, and then returned, the relativistic time difference created between the two ends, the same effect that produced the difference between the airborne and ground-based clocks in the Half-Ailey-Keating experiment, would cause the two mouths to be connected not only across space, but across time. A traveler entering one mouth would emerge from the other at a different point in time. If the time difference were large enough, they could emerge in the past. The paper was published in a leading physics journal, authored by physicists with serious reputations, and it framed the time machine wormhole as a genuine physics problem rather than a speculation to be dismissed. The grandfather paradox, which had previously been discussed primarily as a logical curiosity and a science fiction trope, appeared explicitly in the paper as a problem that the wormhole scenario raised and that physics would need to address. The paper described the problem clearly and noted that it required a resolution at the level of physical law. This was the moment that the grandfather paradox formally entered the peer-reviewed physics literature as a named problem attached to a specific technically developed physical scenario. The 1988 paper was not the first time anyone had taken the physics of time travel seriously, but it changed the texture of the conversation. Thorne had the standing and the publication record that made it difficult to dismiss the subject. An asterisk physical review. Letters asterisk was not a venue that published fringe ideas. The result was that other physicists, including Stephen Hawking and David Deutsch, began engaging with the problem in the peer-reviewed literature, each proposing formal responses to the specific dilemmas the wormhole time machine scenario had made precise. Returning to the question of what the equations permit, the range of conditions under which closed time-like curves appear in solutions to Einstein's field equations is wide. Gödel's rotating universe, Tipler's infinite cylinder, the accelerated wormhole, these are distinct constructions, arrived at by different routes, each satisfying the field equations in its own way. What they share is the curved space-time geometry that general relativity describes. The equations that govern the curvature of space-time around a black hole, and the equations that describe the precession of Mercury's orbit, and the equations that made the Half-Ailey-Keating result predictable in advance, are the same equations that in these configurations produce paths through space-time that return to their own past. This is not a flaw in the equations. It is a feature of the mathematical structure, in the same way that the fact that a sphere's surface is finite but has no edges is a feature of the geometry of spheres. The equations describe a universe in which space-time can be curved by mass and energy, and some curvatures are extreme enough to fold time back on itself. Whether the physical universe prevents these extreme curvatures from forming, or whether it permits them but governs what happens along the closed paths by some additional principle, is the open question that the mathematics alone cannot settle. The Hafele-Keating experiment measured nanoseconds. The GPS satellites accumulate microseconds. The atmospheric muons live tens of microseconds longer than their rest frame decay rate would allow. In each case, the deviation from classical expectations is small enough that it required precise instruments to detect and measure. The deviations are real, confirmed, and consistent with the predictions of special and general relativity at every scale they have been tested. The theory that predicts these small measured differences is the same theory that in its most extreme solutions predicts the closed time-like curves that Gödel described in 1949 and that Thorne's wormhole analysis realized in a traversable physical form. The connection between the two ends of this range, between the nanoseconds lost on a transatlantic flight and the geometry of a space-time that loops back on itself, is the same set of equations applied at different scales and under different physical conditions. The muon that arrives at sea level is a confirmation of the same mathematics that Gödel used to construct his rotating universe. The GPS correction that keeps the maps accurate to a few meters is calculated from the same theory that Tipler used to design his impossible cylinder. The scale changes. The physical circumstances change. The equations do not. There is a sense in which each confirmed experimental result extends the domain over which the theory has been tested, and therefore extends the domain over which confidence in its predictions is justified. A theory that correctly predicts the outcome of the Hafele-Keating experiment and the atmospheric muon detection rate and the GPS clock correction has earned the right to be taken seriously when it produces stranger results in more extreme regimes. The strange results, the closed time-like curves, the wormhole time machines, are strange because the physical regimes they require are extreme, not because the mathematics that produces them is in doubt. The traversable wormhole described in the 1988 paper requires exotic matter with negative energy density. Its throat connects two regions of spacetime across a distance and a time. Its interior is a curved tunnel, the geometry of which can be specified in the equations with the same precision as the geometry of any other region of curved spacetime. The throat's walls are held apart by the negative energy, and without that support, they would collapse under the gravitational pull that general relativity predicts for any concentration of mass and curvature. The requirement is precise and measurable in principle, a specific distribution of matter with a specific sign of energy density, arranged along the wormhole's interior in a way that the field equations dictate. No laboratory on Earth has produced negative energy density at the scale required. The Casimir effect demonstrates that quantum mechanics permits a restricted form of negative energy, but the gap between the Casimir experiment and a macroscopic traversable wormhole is not a gap that current understanding suggests can be closed by any near-term or foreseeable technology. The mathematics says what is needed. What the mathematics does not say is whether a universe that permits such structures in its equations would also permit the physical conditions necessary to realize them. What remains after all the measurements and all the solutions is a picture of time that is considerably more varied than ordinary experience suggests. Clocks on aircraft and clocks on the ground fall out of synchrony by nanoseconds. Satellites accumulate microseconds. Muons live longer than they should. A uniformly rotating universe would fold future pointing paths back into the past, and a traversable wormhole, if the exotic matter required to sustain it could be assembled, would connect 2 times as directly as it connects 2 places. The measurements at the small end of this range are confirmed and precise. The structures at the large end are mathematically sound, experimentally untested, and dependent on physical conditions that remain, for now, beyond reach. The equations themselves do not distinguish between the nanoseconds and the closed loops. They describe what curvature and velocity and gravity do to the passage of time, and they apply the same answer at every scale. The answer at the scale of aircraft and satellites is something that can be measured with atomic clocks and confirmed in the overhead compartments of commercial flights. The answer at the scale of rotating universes and wormhole throats is something that can be written down in a paper and submitted to a physics journal, the mathematics checked and found correct, the physical realization left as a question that the universe has not yet been asked to answer in practice. The interior of a traversable wormhole, in the geometry that Thorne and Morris and Yurtsever described, is a curved tunnel of spacetime. Its walls require something with negative energy density to keep them from falling inward. The requirement is not approximate. The field equations are precise about what is needed, and where, and in what quantity. That precision is the same precision that predicted the outcome of the Hoffele-Keating experiment before Hoffele and Keating drove their clocks to the airport. The mathematics was there, exact and patient, long before the instruments were sensitive enough to confirm it at the scale of commercial aircraft, at the scale of wormhole throats and rotating space-time geometries. The instruments do not yet exist. The mathematics sits, as it always has, one confirmation ahead of what can currently be measured. Stephen Hawking wrote at a desk in Cambridge in 1992, and the paper in front of him proposed something that no one had formally committed to print before, that the universe might be actively protecting itself from its own contradictions. The paper was called Chronology Protection Conjecture, and its central argument was precise and calm and almost domestic in its logic. If the conditions for forming a closed loop in time ever began to develop, if space-time bent far enough back on itself that a traveler could in principle return to their own past, then something else would happen first. The quantum vacuum, which is not empty but fills every cubic centimeter of space with a faint, fluctuating energy that has no mass and no temperature and no settled value, would respond. It would concentrate. Its fluctuations would build on themselves, feeding back through the forming loop, amplifying with each pass until the energy density at that point in space-time rose without limit. The structure needed to complete the loop would be destroyed before the loop ever closed. The universe, in this account, does not permit paradoxes to form. It unmakes the conditions for them at the last possible moment, and it does so with the most ordinary ingredient available, the base-level hum of empty space. What Hawking was proposing was not that time travel was logically impossible. It was that the universe had a physical mechanism for preventing it. The distinction is small and important. A logical prohibition says the thing cannot be conceived. A physical one says the thing fails to occur every time through the operation of specific forces that can in principle be measured. Hawking was offering the second kind of protection, which is quieter and perhaps more reassuring, because it does not ask the traveler to abandon the idea. It simply ensures, through the patient work of quantum mechanics, that the door never quite opens. Empty space in quantum field theory is not the absence of things, it is a condition of constant, unmeasured potential. Fields that do not settle to zero but fluctuate around it, producing particles that appear and vanish before they can be detected, contributing a real energy to every region of space that has nothing in it. This is not speculative. The Casimir effect, measured in laboratories with precision instruments, documents it directly. Two uncharged metal plates brought close enough together feel an attractive force caused by the suppression of certain vacuum fluctuations in the narrow gap between them. The vacuum pushes. It responds to geometry. And in Hawking's conjecture, when the geometry of spacetime begins to curve back on itself in a way that would permit a closed timeline, the vacuum responds to that too, not by pushing plates together, but by building, cycle by cycle through the forming loop, toward a state that prevents the loop from completing. The universe, in this framing, carries its own immune response. The pathogen is the paradox. The immune response is light and energy and the patient accumulation of quantum fluctuation, arriving exactly on time. Hawking acknowledged in the paper itself that the conjecture was not yet proven from first principles. The mathematical machinery for handling quantum fields in curved spacetime near a forming time loop is not simple, and the calculations involved depend on approximations whose validity at extreme conditions remains a matter of ongoing work. What Hawking offered was a framework, a testable, falsifiable physical claim about what the universe would do, grounded in real quantum mechanics and real general relativity, but not yet derived from them with the completeness that a mathematical proof would require. The conjecture sits, still, in the category of well-motivated proposals rather than settled results. Its author treated this as expected. Science at its frontier proceeds that way, by identifying what the answer should be, working out the consequences, and then spending the following decades trying to close the gap between the proposal and the proof. The conjecture remains open. The door it describes remains, for now, effectively closed. Igor Novikov arrived at a different answer, using different tools, and the answer he reached was stranger in one respect and simpler in another. Novikov's framework, developed with colleagues and published in its most complete form in a 1990 paper in Physical Review D, does not prevent the time traveler from arriving in the past. It prevents the time traveler from doing anything that would produce a paradox once there. The principle that carries his name holds that the universe assigns a probability of exactly zero to any history containing an event that contradicts itself. This is not a statement about what the traveler wants to do or intends to do. It is a statement about what the physical equations permit as a realized outcome. The traveler may raise a weapon. The mathematics of the situation will have arranged things through some chain of prior causes, each individually plausible, such that the weapon does not fire. A cartridge fails. A sound from the street causes a flinch at the wrong moment. A third party enters the room by coincidence. The mechanism is never supernatural and never involves the universe reaching in to adjust events by hand. It is simply that of all the possible paths through the situation. Only the ones consistent with a non-paradoxical outcome are physically admissible, and so the physics guides the situation toward those paths, as water finding its level finds it not through intention, but through the geometry of the space available to it. The Novikov self-consistency principle is, in a sense, an extension of something already present in classical mechanics. A ball rolling down a frictionless bowl always ends at the bottom. Not because the ball is trying to get there, and not because the bowl is enforcing a rule, but because the bottom is the only configuration where the forces on the ball sum to zero and motion ceases. Consistency is the attractor. In Novikov's framework, the self-consistent histories of a time travel scenario play the same role. They are the configurations where the causal forces of the situation balance and toward which the physical evolution of events naturally converges. The paradox never arises, not because it is forbidden, but because it is, in the precise technical sense, unstable. The universe does not break the causal loop. It settles into the only version of the causal loop that does not break itself. This has a consequence that is worth sitting with for a moment. In the Novikov framework, the time traveler who goes back to eliminate their grandfather will always fail, but not because they lack the means or the resolve. They will fail because the history they inhabit is one in which they failed, because they exist, which means the grandfather lived, which means something stopped the action, and the something that stopped it will be found, after the fact, to have been perfectly ordinary. A stumble, a misfire, a moment of hesitation that stretched a second too long. The traveler standing afterward in the past, the goal unaccomplished, looking at an outcome that seems to them like bad luck, is from the perspective of the full causal structure, simply the only possible version of that moment. Bad luck and physical law have here the same face. The self-consistency principle asks very little of the traveler and nothing of the universe that it does not already do. It requires no new physics, no novel forces, no exotic mechanism. It requires only that the laws already in place be applied without exception to every point on a closed timeline, including the ones the traveler is visiting. If the laws are time symmetric, if they do not distinguish in their structure between a moment in the past and a moment in the future, then there is no reason to treat the past moment any differently, and no reason for the traveler's actions at that moment to escape the ordinary consequences of physical law. The paradox, in this light, was never a threat. It was a misreading of what physical laws actually permit. Hugh Everett proposed something different, still in his 1957 doctoral dissertation at Princeton, and what he proposed was not a resolution of the paradox, so much as a dissolution of the conditions that make it a paradox at all. Everett's many worlds interpretation of quantum mechanics begins from a simple observation. The standard formalism of quantum mechanics describes systems as existing in superpositions, combinations of multiple possible states, simultaneously, and the equations that govern how superpositions evolve do not, by themselves, contain a mechanism by which superpositions collapse into single definite outcomes. The collapse is added as an additional postulate, a rule layered on top of the formalism to account for the fact that when anyone measures a quantum system, they find it in one state, not in a superposition. Everett asked what the formalism would say if the collapse postulate were simply removed, if the equations were taken at face value all the way through, including during measurement, including when a conscious observer interacted with the system being measured. The answer the equations gave was that the observer, along with the measured system, became part of a larger superposition. Both outcomes occurred. The observer experienced one outcome. Another observer, in the other branch of the superposition, experienced the other. Both branches were real. Neither could observe the other. The universe had not collapsed. It had branched. Applied to the grandfather paradox, this framework removes the loop. The time traveler who arrives in the past and kills the grandfather has not altered their own history. They have entered a new branch of the universal superposition, a world physically continuous with their origin, but causally distinct from it. In that new branch, the grandfather is dead. The traveler's original family line does not develop, and the traveler exists in the past as a being who came from a different branch of reality, not from this one. The traveler's own origin branch continues, undisturbed, in the direction it was always going. The grandfather there continues to live. The traveler there is born in due course. Nothing loops, nothing contradicts. The paradox required a single continuous timeline in which two incompatible events had to coexist, and Many Worlds answers that requirement by providing the events separate timelines in which to unfold without conflict. There is something quiet and almost generous about this solution, considered from a certain angle. It does not prevent the traveler from acting. It does not guarantee that the action fails. It does not require the traveler to be deflected by some improbable sequence of small accidents. It simply places the act and its consequences in a world that can hold them without breaking, a world that by virtue of being separate from the traveler's origin was never the world whose coherence was threatened. The paradox in Many Worlds is a confusion about which world is being discussed. Resolved to its correct referent, it disappears. What Many Worlds cannot provide is the return trip, a traveler who branches into a new world by killing their grandfather in the past has no guaranteed path back to their own branch of origin. The branches do not communicate. The mathematics that describes them does not include a mechanism for crossing from one to the other once the branching has occurred. The traveler in the new world is, in a meaningful sense, a permanent resident, marooned in a timeline they entered from outside, and which will proceed on its own logic without reference to where they came from. This is not a flaw in the solution to the paradox. It is simply a consequence of what the Many Worlds framework actually says about the structure of reality, and it has its own kind of clarity, if not quite its own kind of comfort. David Deutsch spent years thinking about what quantum mechanics actually requires of a consistent description of events near a closed time-like curve, and the answer he arrived at in his 1991 paper in Physical Review D is different in its approach from both Novikov's framework and Everett's. Deutsch's insight began from the observation that classical physics describes systems as being in definite states. A particle is here or there, moving at this speed, in this direction, and at every moment the description is exact and complete. Quantum mechanics replaces this with a density matrix, a mathematical object that encodes not a single definite state, but a probability distribution over possible states, representing the system's actual condition when that condition is not fully determined. In the ordinary course of quantum mechanics, a system in a mixed state, in a superposition of possibilities, will eventually interact with an environment and become correlated with it, effectively settling into a definite outcome in the practical sense, even if the underlying formalism is still tracking superpositions. This is the process called decoherence, and it is why the quantum world appears to us as the definite, classical-seeming world of everyday experience. Near a closed time-like curve, Deutsch argued, the self-consistency condition that Novikov described at the classical level has a quantum mechanical analog. A system entering the past mouth of a closed loop must emerge from the future mouth in the same state in which it entered, because it is the same system and the loop is closed. In classical physics, this requirement is very strict. The system must be in exactly the same definite state at both ends of the loop, which generates paradoxes when the system is something like a time traveler who does something in the past that changes what state they would have been in when they began. In quantum mechanics, the requirement is less strict. The system must be in the same mixed state at both ends of the loop, where the mixed state is a probability distribution over possible outcomes rather than a single definite outcome. And Deutsch demonstrated that self-consistent solutions to this quantum version of the consistency requirement always exist, regardless of the specifics of what happens inside the loop, because the quantum state's flexibility, its ability to encode a range of possibilities simultaneously rather than one definite fact, gives the mathematics enough room to find a solution that closes the loop without contradiction. The density matrix on a page, with its rows and columns encoding the probability of each outcome, and its diagonal entries summing always to 1, is a quiet object. It does not announce the resolution it provides. It simply contains, in its structure, the fact that the probabilities are real and that they are exhaustive, that all possible outcomes are accounted for, that the total is complete, that nothing is missing and nothing is duplicated. Deutsch's self-consistent solution for a quantum system near a closed time-like curve has exactly that character. The resolution is not dramatic. It is a set of numbers that satisfies the equations arrived at through the normal procedures of the mathematics, without requiring any additional postulate or any new physical ingredient. What is strange is not the solution. What is strange is how much room quantum mechanics turns out to have for situations that classical physics cannot accommodate at all. Kip Thorne and his colleagues approached the grandfather paradox through a much more tangible object, a billiard ball. The scenario was a thought experiment, published in a 1990 paper in Physical Review D, in which a billiard ball is placed on a table that contains a small wormhole, a shortcut through space-time connecting two different moments, constructed in the manner that Thorne and his colleagues had shown to be mathematically possible in their earlier work. The ball is given a push along a particular trajectory. The question is whether the ball's path through the wormhole to its own past can result in the ball emerging from the past end and colliding with its earlier self in a way that would prevent the earlier self from entering the wormhole. A billiard ball version of the grandfather paradox, clean and mechanical and stripped of all the emotional complexity of a human actor. What Thorne and his colleagues found was that for every initial trajectory that would produce a paradoxical outcome, every push of the ball that would, if followed classically, cause the earlier ball to miss the wormhole, there existed at least one self-consistent classical trajectory in which the ball's emergence from the past simply redirected the earlier ball into the wormhole entrance rather than away from it, producing an outcome where the collision happened, and yet the ball still entered the wormhole and traveled back to cause the collision. The geometry of the situation, examined carefully, always contained at least one such consistent solution. The paradox did not arise from the mathematics. It arose from selecting only the paradoxical branch and ignoring the self-consistent ones, which the mathematics did not prefer. This was not the same as proving that the consistent solution would necessarily be selected. It was proving that it exists, that the space of possible histories always contains at least one self-consistent option, which means the universe is not being asked to do something impossible. Whether the physical world would select among the consistent options by some additional mechanism, or whether Novikov's probability zero assignment to inconsistent histories would do the work of selection, or whether quantum mechanics would blur the distinction between branches in the way Deutsch described, those questions remained open. What was closed definitively by Thorne's billiard ball analysis was the suggestion that no consistent solution exists. There is always a way for the table to arrange the ball's path that does not produce a contradiction, and the table in this framework will always find it. The image that stays with this result is simple: a billiard ball moving across a felt surface, its trajectory a line of physical law, the wormhole's mouth at one corner of the table like a small dark aperture through which the ball may pass, and, passing, return. The ball that emerges from the passed mouth nudges the earlier ball not away from the entrance, but precisely into it. The geometry closes. The timeline is consistent. The same ball has entered and emerged and nudged itself and entered again, and in the quiet logic of the self-consistent solution, there is nothing left to resolve. The past and future have agreed. There is a term sometimes applied to this kind of scenario, the self-healing timeline, or the resilience of history, and it captures something that the formal mathematics leaves implicit. A history that has actually occurred is in some sense already defended against being undone, not by any agent and not by any intention, but simply because it is what happened, and the conditions that produced it are part of the same space-time structure that any traveler trying to alter it would inhabit. To unmake something that has already been made requires acting against the causal fabric that made you possible. The mathematics, examined carefully, tends to show that the fabric resists, not by applying force, not by pushing back in any mechanical sense, but by not having any self-consistent version of itself in which the undoing succeeded. The thread, followed all the way back, always turns out to have been woven in. The four approaches, Hawking's quantum vacuum surge, Novikov's probability assignments, Everett's branching worlds, and Deutsch's quantum density matrices, do not agree with each other in their conclusions. They are not different ways of saying the same thing. Hawking prevents time travel from occurring. Novikov permits time travel, but steers it toward consistent outcomes. Everett permits time travel, and any action the traveler takes, distributing the consequences across separate worlds. Deutsch permits time travel and any action, finding self-consistent solutions in the quantum probability structure rather than in the classical sequence of events. A physicist who finds one of these frameworks convincing will find one or more of the others less compelling, and the disagreement is genuine. It is not merely a matter of vocabulary or emphasis, but of substantive claims about what quantum mechanics means and how physical law operates near extreme curvatures of spacetime. What they share is more interesting than what divides them. Each framework takes the grandfather paradox seriously as a physical problem. Each applies the formal machinery of real physics, quantum field theory, general relativity, the density matrix formalism, the many worlds interpretation of measurement, to a question that might have been dismissed as a fiction writer's puzzle. Each arrives at an answer that does not require the paradox to be simply forbidden by decree, and each, in its own way, suggests that the universe has more than one resource available when the problem of self-defeating causation arises. The quantum vacuum, the probability structure of history, the branching of worlds, the flexibility of the mixed quantum state. Any one of these would be sufficient. The fact that all four have been proposed, each from rigorous starting points, might be read as evidence that the universe has more room for self-correction than the classical image of a single definite timeline would suggest. The disagreement between these frameworks is exactly what science working at its frontier looks like. The questions they address are at the limit of what current mathematical tools can resolve with precision. The experiments needed to distinguish between them are in most cases not currently performable. The conditions they describe require configurations of matter and energy that no laboratory on Earth approaches. This is not a failure of the science. It is the science doing what it does at its edge, identifying the questions precisely, proposing rigorous answers, and continuing to work out the consequences while waiting for better tools and better observations to close the gap between what the frameworks predict and what can be measured. The gap is wide. The work continues. The question remains, clearly stated, open without being inert. Hawking's conjecture, specifically, has attracted the most sustained critical attention since 1992, and the picture that has emerged from that attention is neither simple confirmation nor simple refutation. Different space-time geometries, when analyzed carefully, produce different results for the quantum vacuum's behavior near a forming closed time-like curve. Some analyses find the divergence Hawking predicted. Others find that the vacuum energy remains bounded, which would mean the protection mechanism fails in those geometries. The calculations are difficult, and their validity depends on the accuracy of approximations used when exact methods become intractable. What the subsequent literature has established is not that Hawking was wrong, but that the conjecture's truth may depend on details of the space-time geometry that a single broad claim cannot cover. The universe's immune response, if it exists, may be more local and more conditional than the original proposal suggested, effective in some configurations, less so in others, and requiring a more careful analysis to assess in each specific case. Novikov's principle faces a different kind of scrutiny. The claim that the universe assigns zero probability to paradoxical histories is a claim about probability, and probability in physics derives from something, from quantum amplitudes, from the structure of the quantum state, from a well-defined measure over possible histories. The Novikov principle, stated as a postulate, does not specify what gives it its force. It names the result. Paradoxical histories are excluded, without fully deriving that result from deeper principles. This is not a fatal objection. Physics proceeds by postulate, especially at the frontier, but the derivation that would show, from first principles of quantum mechanics and general relativity, exactly why and how paradoxical histories come to have zero probability remains a project in progress rather than a completed argument. What Novikov established is a consistency requirement. What explains that requirement at the deepest level is still being worked out. Everett's many worlds framework carries its own unresolved questions, the most persistent of which concern what it means for probabilities to be real in a theory where all outcomes occur. In a single-world quantum theory, probability tells you the likelihood that this world will evolve into a particular outcome. In Everett's framework, all outcomes occur in different branches, and the probability of a branch is something like the fraction of the total quantum weight that branch carries, a measure derived from the mathematics, but whose physical meaning, in terms of how an observer experiences outcomes, has been debated continuously since 1957. The debate has not resolved. The framework remains a serious and minority position in the foundations of physics, held by a significant number of working physicists and contested by a comparable number. Applied to time travel, it produces the cleanest resolution of the paradox. The branching simply removes the contradiction by separating its components, but the resolution inherits all the unresolved questions about what many worlds actually says about probability and the experience of observers. And Deutsch's quantum consistency condition, while mathematically precise and genuinely illuminating, has been questioned on the grounds that the density matrix self-consistency it requires may not be derivable from a standard quantum mechanical treatment of closed time-like curves without additional assumptions about how quantum systems evolve through a causal loop. The paper is rigorous within its assumptions. The assumptions themselves have attracted scrutiny. This, too, is the normal condition of frontier physics, not a crisis but a research program. a set of questions that have been precisely identified and are now being carefully addressed. Sitting with all four of these frameworks at once, there is something that feels less like confusion than like depth. The specific kind of depth that comes from a problem that has been examined seriously by serious people using different tools and producing different but overlapping answers. The grandfather paradox, which began as a logical puzzle in a magazine letter column, and then in a French novel, and then in a formal paper on quantum mechanics, has generated a body of careful physical thought whose variety is a sign not of failure, but of seriousness. Each framework reveals something about the structure of time and causation that would not be visible without the paradox to press against. The paradox is not solved, in the sense that physicists have not reached consensus on which framework correctly describes what would happen near a forming closed time-like curve. But the space of possible answers has been mapped with considerable precision, and the map is not empty. There is a billiard ball on a table in a thought experiment, its felt surface quiet under the lights of an imaginary laboratory. The wormhole's mouth at the corner like a small dark window into last Tuesday. The ball rolls toward it with a speed and angle determined by some initial push given long enough ago that its origin is not quite visible from here. What happens next depends on which framework is correct. In Hawking's version, the wormhole never forms. In Novikov's, the ball enters and emerges and nudges its earlier self along a consistent path, and the table settles into the only arrangement of trajectories that does not contradict itself. In Everett's, a branch opens at the moment of entry, and the ball proceeds in two worlds that no longer communicate. In Deutsch's, the ball exists near the wormhole in a mixed quantum state whose probability distribution satisfies the self-consistency condition, and the numbers on the page sum to 1. In all four versions, the table is not disturbed. The felt is smooth. The lights are still. Whatever resolution the universe applies to the situation, it applies it without drama, without announcement, without anything that would look from the outside like a paradox having been resolved. The ball moves. The geometry holds. The past and the present are somehow consistent with each other, or they are kept from becoming inconsistent by a mechanism that operates below the threshold of observation, or they branch into separate realities that each remain consistent within themselves. The outcome is, in each case, a universe that coheres, not because coherence was forced upon it, but because the mathematics of the situation followed honestly, without cutting corners, without ignoring the less tractable branches of the solution, turns out to have more room in it than the paradox requires. The universe, working quietly at the level of probability distributions and quantum vacuum fluctuations and the geometry of consistent histories, appears to have more than one way of keeping its own accounts in order. The accounts balance, the numbers come out, the billiard ball arrives where the equations say it must, by whichever of the roots remains open, and rests there in the quiet geometry of a self-consistent solution, the table undisturbed, the lights above it still. A GPS satellite passes over a city in the early hours of the morning, its body catching no sunlight at this latitude and season, moving through orbital darkness at roughly 14,000 kilometers per hour. Inside it, an atomic clock is ticking. The clock is extraordinarily precise, precise enough that the difference between its rate and the rate of an identical clock sitting in a building on the ground below is not only measurable, but operationally significant. That difference is 38 microseconds per day. It sounds small. Left uncorrected, it would cause the satellite's position calculations to drift by roughly 10 kilometers every 24 hours, and every telephone using the system to navigate would quietly, reliably lead its owner in the wrong direction. The correction is applied every day. It has been applied every day since the system became operational. The engineers who designed it knew it would be necessary before the first satellite was launched because the equations that predicted the discrepancy were written down in 1905 and 1915, and by the time anyone was building orbital navigation systems, the mathematics had been confirmed so many times and in so many different ways that not applying the correction would have been a straightforward engineering error. The 38 microseconds is not an anomaly. It is not a puzzle. It is a number that was calculated in advance and then measured and found to match, and it appears in the operational specifications of every GPS satellite ever placed in orbit. The number itself has two parts, and they work in opposite directions. Because the satellites orbit at 20,200 kilometers above Earth's surface, they sit higher in Earth's gravitational field than a clock on the ground does. Gravity, it turns out, slows time. The stronger the gravitational field, the more slowly a clock runs relative to one in a weaker field. At orbital altitude, gravity is weaker than at the surface, which means the satellite's clock runs faster. The calculation gives roughly 45 microseconds gained per day from this effect alone. At the same time, the satellite is moving at high orbital velocity, and motion slows time relative to a stationary observer. That effect subtracts approximately 7 microseconds per day. The net result, 45 minus 7, is the 38 microseconds that the engineers correct for every morning. Both effects are real, both are measured, and both must be accounted for simultaneously, or the system fails. A person using a map application to find a coffee shop 2 streets away is, without knowing it, the beneficiary of relativistic physics applied as routine engineering. The coffee shop is where the map says it is, because someone calculated how gravity and velocity each bend time at different rates, confirmed those calculations against measurements from atomic clocks, and built the correction into the satellite before it left the ground. The physics is not decorative, it is structural. Remove it and the system breaks. There is a particular quality to a measurement that was predicted before it was made. The prediction is written down, the experiment is run, and the number that comes back matches the number on the page. Not approximately, not roughly, but within the margin of what the instruments can resolve. That quality is different from simply finding out that something is true. It is more like watching a lock open because someone already knew the combination, wrote it in a notebook, and handed the notebook to the person at the door. The notebook for relativistic time dilation was written in the first decades of the 20th century, and the door has been opening to the predicted combination ever since. Atomic clocks are a useful instrument for making this visible because they are accurate enough to register time differences that would be invisible to any clock built before the 20th century. A cesium atomic clock keeps time by counting the oscillations of radiation emitted by cesium atoms transitioning between two specific energy states, a process that occurs at just over 9 billion cycles per second, reliably enough that the second itself is now defined in terms of it. Two such clocks, set to the same time and then separated, one flown east on a commercial aircraft, one left on the ground, will show different times when they are reunited. The difference is small. It is also exactly what the equations predict for the altitude and speed of that particular flight, and it has been measured directly. The aircraft carrying the clocks is not a laboratory instrument. It is a commercial passenger plane with overhead bins and a beverage service and passengers who have no particular interest in what is sitting above their seats. The clocks sat in those bins on a flight that curved eastward over the Atlantic and they lost approximately 59 nanoseconds relative to the ground-based reference. On a westward flight, different velocity and direction relative to Earth's rotation, they gained approximately 273 nanoseconds. Both results were consistent with the predictions to within the measurement uncertainty of the instruments. The clocks themselves did not know they were participating in an experiment. They simply ticked at the rates that physics required, and the numbers they reported back were the numbers the equations had specified in advance. The muon is a particle that resembles an electron in most respects, but is considerably heavier and unstable. Left to itself, a muon at rest decays into other particles in an average of about 2.2 microseconds. That is not a long time, 2.2 millionths of a second, and it places a strict limit on how far a muon can travel before it ceases to exist. At speeds close to, but not quite at the speed of light, traveling 2.2 microseconds before decaying, a muon can cover at most a few hundred meters. Cosmic rays striking the upper atmosphere at altitudes of 10 to 15 kilometers create muons continuously. The muons should, by the calculation, decay long before they complete the 15-kilometer journey to the ground. They should not be detectable at Earth's surface in any significant number. They are detectable at Earth's surface in significant numbers. This has been confirmed repeatedly and precisely at surface detectors around the world and at particle accelerators, where the same physics can be studied under controlled conditions. The reason is time dilation. A muon traveling at 99.7% of the speed of light experiences time passing at a different rate than an observer at rest on the ground below. From the ground's perspective, the muon's internal clock, the process that governs when it decays, is running more than 20 times more slowly than it would if the muon were at rest. A lifetime of 2.2 microseconds at rest becomes a lifetime of more than 40 microseconds in the ground frame at that velocity. 40 microseconds at that speed is enough time to cover the full 15 kilometers and arrive at the surface. The muon does not experience itself as living longer. In the muon's own frame, if one imagines the muon as having a frame of reference, the muon's lifetime is still 2.2 microseconds. What changes is the length of the path it needs to travel. The atmosphere itself, from the muon's perspective, is length contracted, compressed along the direction of motion, so that what is 15 kilometers in the ground frame is less than a kilometer in the muon's frame. Both descriptions, the ground frame and the muon's frame, give the same physical result. The muon reaches the surface. Time and space adjust together, and they adjust in exactly the amounts that the Lorentz equations specify. The muon does not know about the Lorentz equations, and the equations do not know about the muon. They agree anyway. At particle accelerator facilities, this same effect has been measured with high precision for muons and other unstable particles moving at known velocities. The observed lifetimes of the particles, as measured in the laboratory frame, extend in proportion to their speed, and the extension matches the Lorentz factor calculated from that speed. The measurements are not approximations. They are not consistent in a rough or general sense. They match to the precision of the instruments used to make them, and the instruments are very precise. The data from these experiments accumulates over decades of operation, and the pattern is the same in each new data set. Particles moving faster live longer in the laboratory frame, and the amount by which they live longer is the amount the equations predict. The question of what causes this, what it means, in some deeper sense, that motion slows time, is a different kind of question, and not one that the measurements themselves answer. What the measurements do is establish the fact, firmly and repeatedly, that it happens. A muon entering the atmosphere at 15 kilometers altitude and detected at a sea level instrument has demonstrated, by its arrival, that the time it experienced on its journey was not the same as the time elapsed on the ground below. This is not a theoretical prediction awaiting confirmation. It is a measurement taken again and again at multiple facilities under varying conditions, always returning the same answer. There is an experiment that comes at this question from a different direction, and it involves light rather than particles with mass. John Archibald Wheeler proposed it in 1978, and it concerns a photon, a particle of light, traveling through an interferometer, a device that splits a beam of light into two paths and then recombines them. The standard expectation in classical physics was that a photon would take one path or the other, and the choice would be made when the photon entered the device. Wheeler's insight was that quantum mechanics allowed for a more unsettling possibility. He suggested that an experimenter could delay their choice of how to measure the photon, choosing between a measurement that would reveal which path was taken and one that would reveal interference between both paths until after the photon had already entered the apparatus, and perhaps after it had already committed to whatever behavior it was going to exhibit. What Wheeler proposed was that the photon's past behavior, which path it appeared to take, whether it appeared to take both paths at once, would always be consistent with the measurement choice made after the fact. The photon would not be caught having done one thing and then forced to report another. Instead, the history of what it did would conform to the choice of how it was measured, even when that choice was made after the photon had already traveled through the device. This was a prediction, not an observation, when Wheeler proposed it. It follows directly from the quantum mechanical description of photon propagation, but it is strange enough that direct experimental confirmation was worth pursuing. Carroll Alley and colleagues confirmed it in laboratory conditions in 1984 using a setup that allowed the measurement choice to be made after the photon had passed through the interferometer's beam splitter. The results matched the quantum mechanical prediction. The photon's behavior, as determined by the measurement, was consistent with whichever choice had been made after it had already traveled through the apparatus. There was no detectable mismatch between the late measurement choice and the earlier behavior it implied. The photon did not produce evidence of having done something different before the choice was made. The experimental setup for demonstrating this cleanly requires careful design because there are alternative explanations, loopholes, in the technical vocabulary that a poorly designed experiment might fail to exclude. Perhaps the measurement apparatus was influenced by the photon before the supposedly delayed choice was made. Perhaps the photon carried hidden information determining its behavior from the start. Ruling out these alternatives requires tightening the experimental conditions until the only remaining explanation is the quantum mechanical one. Alan Aspect's research group, working in 2007 and publishing in the journal Science, confirmed the delayed choice prediction using entangled photon pairs in a setup designed specifically to close the most significant loopholes. The results were consistent with quantum mechanical predictions, and the loopholes that earlier experiments had left open were addressed. What this means physically is a matter of continued discussion among physicists and philosophers of physics. What it establishes experimentally is clear. The photon's behavior, as revealed by measurement, conforms to the measurement choice, regardless of when that choice was made relative to the photon's transit through the apparatus. The quantum mechanical description accounts for this correctly. Any description that requires the photon to have a definite classical path committed to before the measurement is made does not account for it. The measurements are not ambiguous on this point. They are simply pointing at something that resists the ordinary picture of a particle taking a definite route through space and time. The question of whether the past can be influenced by the future, a property sometimes called retrocausality, is a minority position in the interpretation of quantum mechanics, but it is a minority position that has received sustained serious attention rather than dismissal. Yakir Aharonov and colleagues have argued in papers published in Physical Review Letters and other peer-reviewed journals that the correlations observed in quantum mechanical experiments may be interpretable as future measurement settings exerting an influence on the behavior of particles in the past. This is not the same as sending a signal backward in time, which quantum mechanics does not appear to permit. It is a more subtle claim that the mathematical structure of quantum mechanics may be most naturally understood as involving influence flowing in both temporal directions simultaneously, with the past and the future, each constraining what the other can contain. The claim remains contested. Other physicists interpret the same experimental results without retrocausality, and the debate about which interpretation is correct, or whether the question of interpretation is even a well-formed one, continues in the literature. What is not contested is the experimental data itself. The correlations exist. They are measured with high precision. Multiple interpretations are consistent with them, and deciding between the interpretations requires additional theoretical or experimental work that has not yet been conclusive. The measurements report what they report, and the report is clear even when the explanation is not. There is something useful in holding two things at once, the clarity of a measurement and the openness of its interpretation. A muon arriving at a surface detector has done something measurable and real. The number of microseconds it took to arrive and the number of microseconds its rest frame lifetime predicts are both well-defined quantities, and their ratio is the Lorentz factor for its velocity. This is not open to interpretation in the way that the photon experiments are. The time dilation is there in the data, and there is no competing account that matches the data without it. The photon's behavior in a delayed choice setup is also there in the data, and there the question of what to make of it, whether time flows in one direction or two, whether the future reaches back to shape the past, remains genuinely open, not because the experiments are unclear, but because they are so clear that multiple theoretical frameworks can each describe them correctly. Cesium atoms in an atomic clock transition between energy states at 9,192,631,770 cycles per second. That number is not an approximation, it is the definition. The second is defined as the duration of exactly that many cycles of the radiation corresponding to that transition in cesium-133, at rest at absolute zero. When a cesium clock in a GPS satellite counts those cycles and reports a time, the report is based on that definition. When the same clock at orbital altitude counts the cycles and reports a different time than an identical clock on the ground, the difference between the two reports is not an artifact of how the clocks were built. It is a consequence of where they are and how fast they are moving. The definition is the same, the physics is what differs. Applying the relativistic correction to GPS satellites requires knowing two things precisely: the altitude of the satellite's orbit, which determines the gravitational time dilation, and the orbital velocity, which determines the kinematic time dilation. Both are known. The correction is calculated from them and then checked against the measured discrepancy between satellite and ground clocks, and the calculated and measured values agree. This check happens as part of the normal operation of the GPS system. The agreement is not remarkable to the engineers running the system. It is expected. It is the result that would be alarming in its absence, not in its presence. The photon experiments and the muon measurements and the atomic clock comparisons are not three separate topics. They are measurements of the same underlying structure of spacetime, approached from different directions using different instruments and different physical systems. The cesium clock in the aircraft overhead bin, and the muon arriving at the surface detector, and the photon behaving consistently with a delayed measurement choice, are each making a report about how time behaves in the physical world. The reports are different in their details, but consistent in what they point toward. Time is not a fixed background against which events occur. It is something that physics acts on, something that bends and slows and dilates, and in some theoretical frameworks at least, may not flow exclusively in one direction. The precision of these measurements matters because it makes the physics unavoidable. If the time dilation were in effect too small to measure directly, it would remain a theoretical prediction of uncertain status. The fact that it is large enough to break a navigation system, if uncorrected, places it beyond the domain of theoretical prediction and into the domain of engineering constraint. The fact that muons from the upper atmosphere arrive at the ground in numbers that only make sense if their internal clocks run slowly at high velocity places it beyond the domain of laboratory curiosity and into the domain of observable natural fact. The measurements do not merely confirm the theory, they demonstrate that the theory is describing something that operates in the physical world at scales relevant to instruments humans have built and phenomena humans can observe. There is a cesium clock sitting in a rack in a standards laboratory somewhere right now, ticking at the rate that defines the second, its count accumulating at 9 billion cycles per second, unattended in the middle of the night. There are GPS satellites passing over every part of Earth's surface, their onboard clocks running at rates that have been adjusted to account for where they are and how fast they are moving. There are muons arriving at surface detectors in basements and at mountaintop observatories, their presence there evidence of a journey completed on time, because time stretched to accommodate the distance. None of these instruments are aware of what they are demonstrating. They are simply doing what physics requires, reporting back the numbers that the equations predicted, maintaining the agreement between theory and measurement that has held without exception since the predictions were made. A physicist working in the 1890s, before the special and general theories of relativity existed, would have predicted that the eastward and westward aircraft flights would return atomic clocks showing exactly the same elapsed time as the ground-based reference. That prediction would have been wrong by a measurable amount. The correct prediction required a different understanding of time, one in which time is not the same for all observers, not constant across altitudes and velocities, not a fixed independent dimension along which everything moves at the same rate. That understanding took shape in the first 2 decades of the 20th century, and it has been confirmed every time a relevant measurement has been made since. The GPS satellites, the aircraft clocks, the muon detectors, and the photon interferometers are all in their different ways returning the same answer to the question of whether that understanding is correct. The answer is yes. It continues to be yes. The instruments do not waver on this point, and neither does the physics. There is a kind of quiet in a measurement that has been made and remade and always returned the same result. It is not the quiet of a question answered and closed. The deeper question, what time is, why it behaves this way, whether the flow of time is fundamental or emergent, or perhaps not a flow at all, in the sense that ordinary experience suggests, remains open in a way that no experiment so far has resolved. But the quiet of the confirmed measurement is its own kind of rest. The number is what it is. The clock runs fast by 38 microseconds per day at 20,000 kilometers altitude. The muon arrives at the surface. The photon behaves consistently with the late choice. These facts are settled, and they sit in the record of what has been measured and confirmed, as still as anything in physics can be. The instruments themselves continue their work in the hours when no one is watching them. The atomic clocks in the Standards laboratories count their cycles through the night. The satellites pass over in their orbits, their corrected clocks sending timing signals to receivers on the ground below. The muons come down through the atmosphere continuously, at every latitude and longitude, most of them arriving at detectors that are recording the data, some arriving at ground undetected, all of them completing a journey that only makes sense if time is doing what the measurements say it does. The record accumulates, the numbers hold. The picture that the instruments report, taken together, is of a physical world in which time is real and measurable and different depending on where you are and how fast you are moving, and in which the equations describing that difference have been right, consistently and precisely, for more than a century. Somewhere above the clouds right now, a muon is moving downward through the dark at a velocity close enough to the speed of light that its internal processes are running at a fraction of their rest frame rate. From the perspective of the ground, it will live long enough to complete its journey. From its own perspective, the distance it needs to cross is short enough to complete before it decays. Both perspectives agree on the outcome. The muon arrives. It has always arrived every time the measurement has been made in exactly the numbers that time dilation predicts. And when it completes the 15 kilometers and enters the detector, a quiet pulse of ionization in a column of material designed to record it. What the detector registers is not just the presence of a particle, it is the confirmation, repeated once more, that time runs differently depending on how fast you move through it, and that this is not a theoretical claim awaiting better evidence, but a measured, documented, repeatable fact about the physical world that surrounds everything, all of the time, whether or not any instrument is present to record it. In the opening pages of H.G. Wells' 1895 novel, the time traveler sits in a machine of his own construction, brass fittings, ivory panels, a small saddle for the rider, and pushes a lever forward for the first time. The lamp in the drawing room grows dim. The housekeeper, who had been moving quietly near the doorway, becomes a streak across the air, then a smear, then nothing the eye can fix on. Outside the window, the garden begins to move through its seasons at a speed that makes seasons meaningless, green to brown to white to green, cycling faster and faster until the colors blend into a gray-green continuity, the year itself becoming a texture rather than a sequence. Wells wrote those sentences in a rented house in Woking, in the last years of a century that had not yet been given a word for what he was describing. The machine had no name before he named it. The act of traveling through time had no framework, no vocabulary, no set of questions attached to it, because no one had yet thought carefully enough about what such travel would require or what it would break. What Wells gave to that late Victorian readership was not a solution, it was a premise. The machine existed, the traveler moved. Time turned out to be a dimension one could traverse in the same way one traversed distance, though in a direction the body had never been built to go. The novel did not ask whether such travel was possible, or what would happen to the logic of cause and effect if it were. Those questions came later, and from different directions, and the people who eventually asked them in the most rigorous terms were not novelists but physicists. Working in university offices and submitting their arguments to peer-reviewed journals, that had not yet decided whether the subject was serious enough to deserve their pages. That journey from a rented house in Woking to the pages of physical review letters took almost a century, and it passed through a French pulp magazine, a wartime novel, a rotating universe, and a letter from a novelist who wanted to know if his plot device would hold up under mathematical scrutiny. The drawing room in Wells' novel is the starting point that is most worth dwelling on, because it was the first place anyone arranged all the necessary furniture in one room. Before 1895, time travel existed in folklore, in mythology, in the occasional literary device. The sleeper who wakes in a changed world, the dreamer who visits the past, the spirit that moves freely through centuries. But these were not mechanical, they were not engineered. They did not raise the question of what would happen if the traveler reached into the past and changed something, because the traveler in those older stories was always a visitor, always incorporeal, always without the capacity to act on what they witnessed. Wells' traveler was different. He sat in a thing with levers and dials and a seat for a human body, and he moved, and the world around him responded to his presence. That single change, making the traveler material, making the travel mechanical, making the visitor into a person who could touch things, planted a seed that would take decades to flower into the specific logical problem that physicists eventually named and argued over. The time frame between Wells' drawing room and the first formal articulation of what the grandfather paradox actually was runs to about 36 years. In 1931, readers of a French science fiction magazine called Sciences et Voyages were writing into the letter column about the consequences of traveling back to meet one's ancestors, and one reader had posed the question in its sharpest possible form: what would happen if the traveler, arriving in the past, killed the ancestor before the ancestor could produce children? The question sat in the letter column between advertisements and chess correspondence in dense French typeface, surrounded by the ordinary business of a pulp magazine, whose readers were working through the implications of the stories they had been reading. It was not posed as a formal philosophical problem. It was posed as a reader's question, the kind of thing a person works out on a quiet evening after putting the magazine down and staring at the ceiling. But the question was exact. It had found the right edge of the problem, and once found, that edge would not go away. René Barjavel picked up that edge 12 years later and built a novel around it. The Careless Traveler, published in 1943, followed a scientist named Saint Menu who travels through time using a device called the anacron, a name that sounds like a mistake in the fabric of chronology, which is more or less what it produces. Saint Menu, through a series of actions in the past, threatens the line of ancestors that produced him. Barjavel was writing in occupied France, under conditions that gave the idea of an erased existence something more than an academic flavor, and the novel carries a weight that its logical puzzle alone would not account for. The anacron sits in the story not as a curiosity, but as a consequence, the kind of machine that produces problems precisely because it works exactly as intended. Barjavel did not resolve the paradox, he dramatized it. He let Saint Menu stand at the edge of his own erasure and stare into it, and then he wrote the novel that came out the other side of that stare. It was the first time the grandfather paradox had been the structural center of a book-length narrative, and it would not be the last. The move from narrative to peer-reviewed physics took another 4 decades, and it happened partly because of a letter. Carl Sagan, in the mid-1980s, was finishing a novel called Contact, a story involving a machine built from plans, transmitted by extraterrestrial intelligence, a machine capable of transporting a human being across interstellar distances in a very short time. Sagan was a working scientist, and he was uncomfortable with the idea of publishing a novel that contained a scientific mechanism he had not checked. So he contacted Kip Thorne, a physicist at Caltech whose work on general relativity and the geometry of space-time was already substantial, and he asked, would a wormhole work? Could a tunnel through the fabric of space-time plausibly serve as the transport mechanism in the story he had written? Thorne looked at the mathematics. The mathematics turned out to be more interesting than either of them had expected. Thorne and his colleagues, Michael Morris and Ulvi Yurtsever, published a paper in Physical Review Letters in 1988 demonstrating that a traversable wormhole with one of its mouths accelerated to high velocity and returned would, through relativistic effects, become a machine capable of connecting not just two places, but two moments. The grandfather paradox, which had lived in letter columns in wartime novels and the footnotes of science fiction, arrived in a peer-reviewed physics journal because a novelist wanted to make sure his plot was sound. That arrival changed something. Before 1988, the grandfather paradox was, for most physicists, the kind of problem that belonged to science fiction, interesting as a thought experiment, not serious as a physics problem, because physics had not yet decided that time travel was a subject worth taking seriously. After Thorne's paper, the question was different. The grandfather paradox was now the grandfather paradox, a named problem in the peer-reviewed literature, a thing with a formal designation and a set of proposed solutions, and a growing body of papers that took it as their central subject. The fiction and the physics had been moving toward each other for decades, and the letter from a novelist to a physicist closed the remaining distance in a single exchange. Sagan's novel, published in 1985, had already done something important before the physics caught up. Contact introduced to a wide readership, not a readership that read science fiction magazines, but a readership that read serious literary novels, the idea that the geometry of space might be bent in ways that made distant points adjacent, and that a human being might pass through such a bend and arrive somewhere that was not just far away, but also, depending on how the geometry was arranged, some other time. Sagan wrote the wormhole as a transport mechanism with the specific careful attention of a scientist who knew the difference between a metaphor and a mechanism. The result was a novel that felt, to its readers, like it was describing something that might actually be permitted by physics, even if no one had built it yet. That feeling of being on the edge of something real rather than inside something imaginary was new. Wells' Time Traveler had been a fantasy, even to Wells. Sagan's wormhole was the beginning of a physics problem. The movement of time travel from the imagination into the laboratory is not a clean line. It is more like a conversation that kept changing rooms, from the drawing room in Woking to the letter columns of Paris, from a wartime French novel to a university library in Princeton, from a physicist's desk in Pasadena to a cinema in 1985. That cinema is worth thinking about for a moment. The Back to the Future trilogy, beginning with the first film in 1985 and completing itself with the third in 1990, introduced the logic of what the grandfather paradox actually means, the erasing of the traveler's own preconditions, to an audience that may never have read a word of Wells or Barjavel or Thorne. The specific image of Marty McFly fading from a family photograph in a dark theater, his outline growing transparent as his parents' relationship comes undone, made the paradox's central claim visible and emotionally felt in a way that no physics paper had managed for a general audience. The photograph dimming, the the figure vanishing from it, the edges of the image going blank. This was the grandfather paradox, rendered as something a person in a cinema seat could feel in their chest rather than merely follow with their intellect. Physicists who later wrote for general audiences have acknowledged this. Michio Kaku and Brian Greene, both of whom have published widely read books on the physics of time, have cited the Back to the Future films in those books as the clearest popular demonstration of what temporal paradoxes look like when they are made concrete. This is not condescension, it is recognition of what the films did well. They took a logical structure that was genuinely abstract and gave it a specific face, a specific family portrait, a specific pair of parents who needed to dance together at a high school prom, or a boy would cease to exist. The logic is not perfectly rigorous by the standards of a physics paper, but the emotional shape of the problem is exactly right. Marty McFly's predicament is the grandfather paradox given sneakers and a guitar, and the image of him fading from the photograph has probably introduced the paradox to more people than all the peer-reviewed literature combined. The films also did something subtler, which was to dramatize the Navikov self-consistency principle without naming it. Marty's repeated, exhausting, increasingly desperate attempts to get his parents back together are not simply plot mechanics. They are, in the logic of the story, the universe enforcing the conditions of its own history. The film does not resolve the paradox through branching timelines or quantum states. It resolves it through stubbornness, through the insistence that what happened must happen, that the self-consistent solution will always find a way to assert itself. Igor Novikov, working through the formal mathematics of this principle in the same decade, would have recognized what the film was doing, even if its writers had no idea his work existed. The principle that paradoxes are simply inadmissible outcomes, that history has a resilience, a tendency to find its way back to what it needs to be, is the backbone of the trilogy's plot. Dressed in a DeLorean and driven by a teenager, the relationship between science fiction and scientific thinking about time has never been entirely clean, and it is not always obvious which direction the influence runs. Wells' explicit framing of time as a fourth dimension in the opening pages of The Time Machine reached a reading public in 1895, a full decade before Einstein's special theory of relativity was published. Historians of science have noted this, carefully, without claiming that Wells caused Einstein or that the novel influenced the theory in any direct way. The claim is more modest, that the cultural atmosphere of a society that has already been given a narrative framework for thinking about time as traversable and dimensioned may have been, in some diffuse and unmeasurable way, more receptive to a mathematical reconception of time as the fourth dimension of space-time than it would otherwise have been. Whether this is true is not something that can be established the way a physics result can be established. But the coincidence of timing has been noted, and the observation is not without interest. Einstein himself is part of this story, and not only as the architect of the relativity that made the physics of time so strange. In 1949, his colleague and friend Kurt Gödel, working at the Institute for Advanced Study in Princeton, where the two men were neighbors and regular walking companions, presented Einstein with a paper. The paper contained a solution to Einstein's own field equations, or the mathematically legitimate description of a universe that rotated uniformly, in which the geometry of spacetime was arranged in such a way that an observer could follow a path through it and arrive back at their own past without ever exceeding the local speed of light. The universe in the paper was everywhere threaded with closed time-like curves, loops in time that any sufficiently patient traveler could follow back to their own beginning. Gödel handed the paper to Einstein, and Einstein responded to it in print. His published response acknowledged the mathematical validity of the solution while suggesting, with what has been described as personal discomfort, that physical considerations would rule out such a universe in practice. He did not argue that Gödel was wrong. He argued that the actual universe was probably not like that. The discomfort is worth noting. Here was the man who had built the framework Gödel was working within, sitting across from a proof that his framework permitted something he found deeply troubling, and responding not by rejecting the mathematics, but by expressing a hope about the world. That hope, that the actual universe is not the kind of place where the past can be revisited and altered, is one of the threads that runs from Einstein's walking companion in Princeton all the way to Stephen Hawking in Cambridge in 1992, when Hawking published his chronology protection conjecture and argued formally that quantum vacuum fluctuations would prevent closed time-like curves from forming before any time travel paradox could arise. Hawking's paper was physics at the frontier of what could be calculated. But the impulse behind it, the sense that the universe ought to have a mechanism for keeping its own history coherent, is an impulse that Einstein's discomfort in 1949 already expresses in a less formal register. Hawking returned to this impulse in 2009 in a way that was more playful than his 1992 paper, but no less pointed. He held a reception for time travelers. The invitations were printed and distributed, but only after the event had already taken place, the logic being that genuine visitors from the future would be the only ones capable of receiving an invitation sent backward through time. The champagne was ready, the room was prepared. No one came. Hawking described the event in his documentary series, Into the Universe, with Stephen Hawking in 2010, with the particular kind of dry satisfaction that belongs to a person who has set a trap and is not entirely surprised to find it empty. The empty room was, in its way, a data point, not a proof of anything, but a small, light-hearted instance of what the chronology protection conjecture predicts, that closed time-like curves and the time travelers who would travel through them are the kinds of things the universe does not permit. The champagne remained on the table. The guests from the future did not arrive. Hawking noted this and smiled and moved on. The party invitation sitting on a desk in Cambridge in 2009 is an image worth staying with for a moment. It had a date on it, a date that had already passed. It had an address and a time, and all the ordinary information of a social occasion, arranged as if the logistics of traveling across decades were simply a matter of knowing where and when to go. It was absurd on its face, and Hawking knew it was absurd, and the absurdity was the point. The chronology protection conjecture is a formal physics proposition with mathematics behind it, but it is also, in the right light, a very dry joke about the nature of paradox. The joke is that the test of whether time travel to the past is possible is exactly the kind of test that can never produce a positive result through ordinary means, because if the positive result had occurred, the party would have been attended, and the attending would have been recorded, and we would already know about it. The room was always going to be empty, by the same logic that says the traveler was always going to fail to kill the grandfather. The absence of guests is not a proof. It is a shrug from the universe in the direction of its own consistency. The popular culture of time travel has a long memory and a tendency to loop back on itself, which is fitting. The same images recur across different decades and different media: the photograph that changes, the newspaper with a different headline, the birth certificate that disappears, the face in the mirror that is no longer quite the same face. These are all versions of the same underlying intuition that if the past were changed, the evidence of the change would propagate forward into the present, and the present would be different, and the difference would be visible somewhere. The fading photograph in Back to the Future, the branching family trees in a dozen novels and films since, the grandfather who is and is not there. The intuition is sound, even when the storytelling around it is not rigorous, because it is tracking something real, the actual logical structure of a causal loop, dressed in whatever clothes the story requires. That tracking has been going on for longer than the physics has been formalized. Before Novikov published his self-consistency principle, before Deutsch wrote his 1991 paper on quantum density matrices and closed time-like curves, before Thorne and his colleagues demonstrated that a traversable wormhole could be converted into a time machine, storytellers had been circling the same logical structure and finding that it had the same shape from every angle. The shape is this: a loop with no beginning and no end, in which cause and effect chase each other around a circle and never find a resting point. The grandfather is alive and the grandfather is dead. Simultaneously, by the same act for the same reason, the loop does not resolve, it simply turns. What the physics did over the second half of the 20th century was give that turning loop a set of possible exits. Hawking's exit is that the loop never forms at all. The universe forecloses it before it can close. Novikov's exit is that the loop always finds the self-consistent path, the one that does not produce a paradox, even if that means the traveler always fails, always misses, always arrives a moment too late. Everett's exit is that the loop branches. The two incompatible halves of the paradox are sorted into separate worlds, each complete and internally consistent, never in contact with each other. Deutsch's exit is that the loop exists, but the traveler occupies it in a mixed quantum state, not definitely one outcome or another, but a superposition that satisfies the consistency condition without requiring a classical resolution. These are different exits, and they are exits from different buildings. They do not all agree on what the paradox is, but they agree that the structure has a shape, and that the shape demands a response. The books on the shelf in a university library, their spines facing outward in a row, hold all of this between their covers in quiet proximity. Wells' time machine, with its brass saddle and its flickering drawing room, Barjavel's careless traveler, with its anachron and its threatened ancestral line, written in a France that knew something about lines of descent, being erased. Thorne's black holes and time warps, where the wormhole becomes a time machine in the course of a calculation that began as a favor to a friend. Paul Davies' How to Build a Time Machine, where the engineering requirements are laid out with the specific attention of someone who takes the question seriously enough to cost it out. These books did not produce each other in a simple sequence. They were written in response to different pressures: narrative, logical, mathematical, popular, and they reached different conclusions, or no conclusions at all, about whether time travel is possible or what it would mean if it were. But they are in conversation, across decades and disciplines and languages, about the same cluster of questions. The conversation started in a drawing room that was beginning to blur at the edges, and it has not stopped. The man who began it, Wells, sitting in Woking in the 1890s, inventing a vocabulary for a problem he had not quite formulated, was not thinking about quantum density matrices or closed time-like curves. He was thinking about what it would be like to sit in a machine and move through time the way a ship moves through water. He was thinking about what the garden would look like if the seasons passed at the speed of thought, and what the housekeeper would look like if she moved too fast for the eye to follow, and what the traveler would find when he stopped the machine and stepped out into a world that had become unrecognizable while he sat still. These are not physics questions, they are imagination questions. But they are imagination questions that had physics answers waiting for them. Somewhere in the future that Wells was, in a sense, already traveling toward. The garden outside the window of the drawing room, cycling through seasons at a speed that made seasons meaningless, is the image the novel keeps returning to, and it is worth returning to one more time. In that image, time has become a texture rather than a sequence. The individual moments are still there, but they cannot be distinguished from one another at the speed the machine is traveling. What looks like a blur is in fact an enormous density of distinct events, individual days, individual nights, individual afternoons in which someone walked across the grass and left a print that the following week's rain erased. The blur is not a simplification, it is a compression. The garden in that window contains everything that ever happened in it, overlaid to the point of illegibility. To slow the machine and step out into any particular moment is to unpack one layer of that compression and stand inside it, to be for a moment in a specific day rather than in the blur of all days. This is not how physicists think about closed time-like curves, exactly, but it is not entirely unlike it either. The self-consistency condition that Novikov and Thorne and Deutsch were working toward, the requirement that any history admitted by the equations of physics must be free of paradox, is, in a way, a requirement about which layers of the blur can be inhabited. The paradoxical histories are the ones that cannot be stepped into, the ones that dissolve on approach because they contain within themselves the negation of their own preconditions. The self-consistent histories are the ones that hold still when examined, that remain stable when the machine stops and the traveler steps out and looks around. The garden is only accessible from inside the machine if it is a garden that can actually be visited without ceasing to exist. Wells did not know any of this. He could not have. The mathematics that would eventually be used to describe the geometry of space-time, Einstein's field equations, the topology of Lorentzian manifolds, the density matrix formalism of quantum mechanics, was not available to him, and even if it had been, he was a novelist, not a physicist, and his questions were different from the ones physicists would eventually ask about the same subject. But he was asking questions, and the questions were pointed in the right direction, and the world that the questions implied, a world in which time was a dimension, in which a person with the right machine could move through it in ways that the body had not evolved to go, was the world that the physics eventually had to contend with. Wells conjured the possibility, and the physics spent the better part of a century working out the consequences. The quiet thing about this history, the thing worth holding as the library closes and the lights go down, is that none of it has been resolved. The grandfather paradox is still a paradox. The proposed solutions are still proposed solutions, not established facts. The chronology protection conjecture has not been proved. The Novikov principle has not been tested against an actual closed time-like curve. The many worlds interpretation of quantum mechanics remains an interpretation, contested and debated, and without consensus. The wormhole required to build a time machine still requires exotic matter that no one knows how to produce. The question that a reader in France posed in a letter column in 1931 is still, in the precise sense of the word, open. The circle with the arrow has not found its stable resting point, and the books remain on the shelf. Wells' Time Machine, its pages yellowed to the color of old cream. Barjavel's novel, written in a language that makes the word for time, temps, rhyme with the word for weather, as if the French have always known that the two are the same kind of thing, variable and inescapable and impossible to hold in the hand. Thorne's book, with its equations laid out carefully for readers who might not be physicists, but are willing to follow the argument patiently. Davies's book, with its engineering estimates and its frank acknowledgement that the engineering is presently impossible and might always be. The spines face outward in their row. The titles are legible. The questions inside them are not going anywhere. After the library closes, in the particular silence that libraries have when no one is in them, a silence that is not empty but full of the muffled presence of all the things the books contain, the books sit in their row and continue their conversation without an audience. The conversation does not require an audience.